Welcome. In the last class we looked at the relationships between some of those properties, thermodynamic properties, using some simple aspects of mathematics. We also saw the Gibbs-Duhem equation, which is a central equation in thermodynamics, since it gives the simultaneous variation with temperature, pressure and chemical potential, which are the fundamental intrinsic properties of a system. We will continue looking at useful relationships between various variables, and I will also tell you how it comes in useful in the tutorial part. The next thing that we are going to look at in the same vein is Maxwell's relations. To get to Maxwell's relations, let us first consider a theorem in calculus that is applicable to exact differentials. We do not have to worry too much about whether we are dealing with exact differentials or not in thermodynamics, because we deal with state functions in thermodynamics mostly, and most of those state functions can be written as exact differentials. The theorem says if f can be considered as a function of some variables which are given here as x1, x2 and so on till xk, then df, f being an exact df being an exact differential, can be written as dou f by dou x1 at evaluated at all these other variables kept constant, which is indicated by xj as I had mentioned earlier, dx1 plus dou f dou x2 xj, which means x1, x3 and other variables till xk are held constant, that is what this xj means, dx2 and so on until dou f by dou xk all other xj's remaining constant dxk. So, this is a fundamental theorem that is applicable to exact differentials. Now, let us take those partial differentials dou f by dou x1 xj at constant xj, dou f by dou x2 at constant xj and so on, and replace them with another symbol for easy manipulation. Let us say that y1 equals dou f by dou x1 at constant all other xj's. If we do that, then we can write the previous equation as df equals y1 dx1 plus y2 dx2 and so on till yk dxk. Excuse me. Let us call this equation 224. The theorem that was mentioned initially, which is also known as reciprocity relationship, says that when you can do this, that is df being expressed as y1 dx1 plus y2 dx2 and so on till yk dxk, dou yi by dou xn xj at constant xj equals dou yn by dou yn dou xi at all other xj's remaining constant. For example, if you take I to be 1 and n to be 2, dou y1 by dou x2 at all other xj's remaining constant equals dou y2 by dou x1 at all other xj's remaining constant. It is applicable for any I and any n that is not different, that is different from I. For example, it could be dou y3 by dou x10 at all other xj's remaining constant equals dou y10 by dou x3 at all other xj's remaining constant. If we apply this theorem, also called the reciprocity relationship, two are basic equations that we had given earlier, basic differentials that we had given earlier. If you recall equation 212, which is also given here, dut equals T dst minus P dVt plus summation of mu I dni. Remember that this consists of many different terms that are given by the sum sign. If we apply the reciprocity relationship here, it will give us dou t by, let us choose this to be the other variable, dou Vt at all other things remaining constant, such as St and all ni's remaining constant. This equals minus dou P, which is related to Vt earlier, dou P dou St at Vt and all other ni's remaining constant. So, this gives a nice relationship between the thermodynamic variables just by using the reciprocity relationship of writing differentials. We will call this equation 226. Let me show this a few more times so that it becomes simpler to remember. Let us consider the next relationship. dgt equals minus St dt plus Vt dp plus summation of mu I dni, as we have already seen in equation 2.15, 215. If we utilize the reciprocity relationship here, one of them, then minus, which comes from here, minus of dou St dou P at constant t and all other ni equals dou Vt dou t at constant p and all other ni. By now you must be getting comfortable with writing reciprocity relationships from total differentials. Let us call this equation 2.27. Let us take another example. I will give you all 4 or all more than 4 in the first case. dht we have seen is T dst plus Vt dp plus summation of mu I dni, and this was equation 217 before. If we write or apply the reciprocity relationship here, dou t by dou t dou p at constant s all other ni equals dou Vt dou St at constant p all other ni, equation 228. Let us consider dat now. We already have equation 218 as dat equals minus St dt minus P dVt plus summation of mu I dni. Now, it must become second nature to you. Dou St dou Vt, note both are minuses here, so you do not have to worry about it if you take these two. Dou St dou Vt at constant t all other ni equals dou Pt dou t at constant Vt all other ni. We will call this equation 229. Let us consider equation 215 again. Earlier, for all the 4 equations for a closed system, we looked at just the first 2 terms for writing the reciprocity relationship. Now, let us look at the third term also. Note that this consists of the sum, so each one is different here. So, let us take one of those, dou mu I dou t at all dou mu I dou t at constant p all ni equals minus dou St dou ni at constant T p and all nj's apart from this ni. Let me repeat this, dou mu I dou t at constant P all other Ni equals minus is here dou St dou Ni constant T P all other Nj's which are different from I. Let us do this once again to get other useful relationships. Before that, let us call this equation 230. Dou mu I dou P at constant T all Ni equals dou Vt dou Ni at constant Tp all Nj's different from Ni remaining constant. We had considered these two terms while writing this equation. Let us call this equation 231. There was a reason why we chose to compare these two and these two and actually use dgt to do it. If you recall, we have dgt with variation of T, P and Ni, so which are easily measurable variables. If they are easily measurable, then you can do experiments with them quite easily. This gives the variation of chemical potential with temperature, which is a very useful relationship to have when the pressure and the number of moles of all species are held constant, which can be done experimentally. This gives the variation of chemical potential with pressure when the temperature and all moles are held constant, which can be again done in an experiment, and this is given in terms of the other thermodynamic variables which may be easier to determine. So that is going to be some sort of a theme in this particular module, that is expression of difficult to measure thermodynamic variables in terms of easy to measure thermodynamic variables. That is the way we are going to use these equations. These equations are valid for anything that you want to do. These relationships are there for anything that you want to do. We are going to do one small aspect or one aspect of the many different things that you can do with these relationships. The equations 226 to 231, let me go back and show you 226 just for a recall. 227, okay, 226 was dou T dou Vt constant St Ni equals minus dou P dou St constant Vt Ni. 227 minus dou St dou P at constant T Ni equals dou Vt dou T at constant P Ni, equation 227. 228 was dou T dou P constant S Ni equals dou Vt dou St constant P Ni, and equation 229 was dou St dou Vt constant T Ni equals dou P dou T at constant Vt Ni. And as we spend some extra time here, dou mu I dou T at constant P Ni equals minus dou St dou Ni at constant Tp all other Nj's, and dou mu I dou P at constant T Ni equals dou Vt dou Ni at constant Tp all other Nj's. So these equations are called Maxwell's relations, very useful. As I had already mentioned, it is worth mentioning again, temperature, pressure and the total volume are easily measurable. Maxwell's relations can help us, that is one of the things that they do, you can do many other things with them, can help us express the other variables such as Ut internal energy, St enthalpy, total enthalpy, all these are total quantities since there are more than 1 mole of the substance, of the pure substance that we are considering here. Ht is enthalpy, total enthalpy, At is total Helmholtz free energy, and Gt is total Gibbs free energy. All these can be written in terms of easily measurable T, P and total volume, and therefore by these measurements under suitable conditions we can estimate these thermodynamic variables ut, st, ht, at and gt. We started with a slightly more general set of relations. The Maxwell's relations that we have written down so far are valid for any system, any pure substance, irrespective of the size of the system or the number of moles in the system. Whereas in many different books, including your textbook initially when this is introduced, you would find the Maxwell's relations written for 1 mole, which means the mu I dni terms, any dni related terms, ni related terms will not be there because you have only 1 mole and that is held constant. Let us look at these relationships for completeness, because you can directly use these relationships under such conditions where you have 1 mole of the substance. Dou T by dou V constant S equals minus dou P dou S constant V. This was obtained by applying the reciprocity relationship to the total differential written for 1 mole of the substance. Dou T dou V at constant S equals minus dou P dou S at constant V minus dou S dou P constant T equals dou V dou T constant P, dou T dou P constant S equals dou V dou S constant P, and dou S dou V constant T equals dou P dou T constant V. You would want to compare these expressions. I would like to do that, I do not want to go back now. I would let you do that. If you just compare these expressions with the earlier Maxwell's relations that we have written, you would see that these are exactly the same as the first 4 Maxwell's relations that we had written, except that you do not have any ni's occurring because we have 1 mole of the substance. These would come in handy in some of your problems in the university exams and so on. Okay. Now we are going to do some tutorial work. I am going to present this problem to you and then I will give you some time to work it out, because you will understand the application of these equations and get more comfortable with the applications of these equations only by working out problems, and you need to work them out first. That will be the most effective. So you will work them out, I will give you time, maybe about 10 minutes, and maybe after some time I will present a part of the solution so that you can start working at a faster pace if that hint or a part of the solution is going to help you, and later I will give you the entire solution. This exercise essentially shows the way to use some of the relationships that we have developed so far. The question is, for a closed system, express in terms of easily measurable properties, pressure, total volume and temperature, the variation of internal energy with volume for a process in which the temperature and the number of moles are held constant. Essentially we are looking for dou ut, the variation of internal energy, with volume. So dou ut dou Vt at constant temperature and Ni. Please go ahead, you have about 10 minutes. Let us look at the at a part of the solution now. To do this, you know that we are looking for dou ut dou Vt. Let us begin with equation 212, okay, because this has the relationship for dut, and these would be dou ut and so on, dou ut variation. We know that dut equals T dst minus P dVt plus sum over all terms I mu I dni. The partial derivative of V at constant T and Ni can be written as dou ut dou Vt T Ni T dou St dou Vt minus P dou Vt dou Vt T Ni plus summation over all I mu I dou Ni dou Vt at constant T Ni. Continue further, we are looking at dou ut dou Vt at constant T Ni. Look at these terms here and see what you could do to get it in terms of measurable quantities. Take another 5 minutes or so. Let us continue with the solution. Look at the second and third terms on the right hand side here, minus P dou Vt dou Vt T Ni plus summation of mu I dou Ni dou Vt at constant T Ni. The second and third derivative terms on the right hand side are 1 and 0, 1 because dou Vt dou Vt, so that goes to 1, and 0 because Ni is a constant, so any variation with Ni would be 0. Therefore, what remains of that equation is dou ut dou Vt at constant T Ni, this was the initial left hand side, the first term remains equals T dou St dou Vt at constant T Ni, and since this has gone to 1, whatever accompanied P here, we just have P remaining minus P. So, dou ut dou Vt at constant T Ni equals T dou St dou Vt constant T Ni minus P. Now, if we use one of the Maxwell's relations, which is equation 229 here, dou St dou Vt, now this is a little difficult to measure, so let us try to write this in terms of easily measurable quantities. Dou St dou Vt at constant T Ni equals dou P dou T at constant Vt Ni. In this case P T are all easily measurable. If you do that, then you can write dou ut dou Vt at constant T Ni, which is what we need, equals T, this we are going to replace with this dou P dou T at constant Vt Ni minus P. Equation 232, let me call this equation 232 because it will come in useful later, which is actually the needed relationship. We have gotten this in terms of all easily measurable thermodynamic variables T, P, Vt, Ni and so on. Okay, to recapitulate, the easily measurable ones are Pt, V the molar volume, or Vt the total volume. In addition, the following are measurable and the data is available in the form of tables or figures in books, handbooks or papers for pure substances. Some of these are available at the back of your textbook, Smith, Van Ness and Abbott 2. Cp, heat capacity at constant pressure, this is available, the data is available. Cv, heat capacity at constant volume, the data is available. Alpha, which is expansivity, I will go into details of this in a little while, and kappa, the compressibility, are all available. So, if they are available, we might as well make use of them to estimate the difficult to measure thermodynamic variables. In addition to these, the latent heats are all available, as well as the heats of reaction are available. Let us look at these in a little more detail. Other measurable thermodynamic variables. Heat capacity Cp is defined as dou H dou T at constant P. This is for a pure substance. We will call this equation 233. For any system, Cp is defined as dou Ht dou T at constant P. This is for 1 mole of a pure substance, this is for any system. Now, Cv is defined as dou U dou T. Cp was dou H enthalpy dou T, Cv is dou internal energy dou T at constant volume. Since this is V at constant volume, we call it Cv, specific heat at constant volume. This is for a pure substance, we will call this equation 234, and for any system you can define Cv as dou Ut dou T at constant V. Expression of the not so easy to measure thermodynamic properties in terms of measurable thermodynamic properties helps in estimation of the not so easy to measure ones. I am just repeating this so that it gets across. The exercise was for a closed system consisting of 1 mole of a pure substance, express in terms of more easily measurable properties the variation of enthalpy and entropy with temperature and pressure respectively. In other words, dou H dou T at constant P, dou S dou T at constant P, and just the flip with P and T, dou H dou P at constant T, dou S dou P at constant T. The way to go about this would be as follows. The first partial derivative was dou H dou T at constant P. If you go back into your notes or into the earlier slides of this lecture, you would actually find that this is the definition of Cp, which is a measured quantity, which is the data of which is available. So, we do not have to do anything further. Dou H dou T at constant P is itself a measured quantity. Since the system consists of 1 mole of a pure substance, if you look at the equation 2.6 that we had written earlier, we can write the same equation 2.6 given here, dH equals TdS plus VdP. This is for a closed system consisting of 1 mole of a pure substance. Now, if we take the partial derivative of H with respect to T at constant P, dou H dou T at constant P, the first term will be T dou S dou T at constant P, and the second term is going to vanish here because we are forcing P to remain constant. Therefore, dP will go to 0 and this term would vanish. Therefore, dou H dou T at constant P equals T dou S dou T at constant P. Proceeding further, dou S dou T at constant P equals Cp by T. This you get by comparing the previous equations. Let us go back a little bit. This is dou H dou T at constant P equals Cp, dou H dou T at constant P, we had gotten this as T dou S dou T at constant P. You equate this to this, Cp is easily measurable, and therefore we get dou S dou T at constant P equals Cp by T. So, we have handled this also. We will call this equation 235. So, we have some more remaining. The variation of entropy S with respect to pressure at constant temperature, dou S dou P with T remaining constant, is actually given by a Maxwell's relation. You go back to your we had written all 4 equations for 1 mole of a pure substance. You can go back and look at that. Actually equation 227 written for a 1 mole was dou S dou P at constant T equals minus dou V dou T at constant P. Let us call this as equation 236 here, and therefore that takes care of 3 different parts of the question. There is one more part that is remaining. For that, let us consider H as a function of S and P. You can consider whatever as function of the relevant variables. In this case, let us consider enthalpy as a function of entropy and pressure. If you do this, dH can be written as dou H dou S at constant P ds, dou H dou P at constant S dP. Now, if you take the partial of that with respect to P at constant temperature, dou H dou P at constant T, this is the quantity that we need, is dou H dou S at constant P, which is the first term that came from the previous total differential writing, and of course dou S dou P at constant T, and this again comes from the partial differential writing, the total differential expansion dou H dou P at constant S, and here dP would be there. You take the partial derivative dou P at constant T. Very easy to see that this goes to 1. Now, comparison with the terms on the right hand side of the total differential, dH equals TdS plus VdP. This is the total differential of dH. We can write that dou H dou S at constant P equals T, and dou H dou P at constant S equals V. Therefore, dou H dou P at constant T, which is the one that we require, is nothing but T dou S dou P at constant T plus V. So, we have gotten all 4 quantities that we were required to get. If you look at it, it was essentially manipulation, appropriate manipulation of the mathematical relationships to get whatever we needed. This is still in terms of dou S dou P at constant T, and this is not completely in terms of easily measurable variables, but using the relationship between dou S dou P at constant T that we had given in equation 235 earlier. You can look at equation 235, we have numbered that, yeah, dou S dou T at constant P is Cp by T. We can write dou H dou P at constant T equals minus T dou V dou T at constant P plus V. This is the other relationship which brings dou S dou P at constant T in terms of V, T and P. We will call this equation 237. See you in the next class.